Hey guys, what's going on? So today we're going to be talking about rundown on gauge theory and Maxwell's theory. In the next video we're going to be doing the same thing but with Yang-Mills theory, because this is all going to tie in to our understanding of quantum gravity and how we've been formulating quantum gravity so far. Right, so with that being said, make sure to hit that like and subscribe button. You can go into my Patreon page if you want to see the full videos. If you just want to see the 6-minute videos-ish that I'm putting up on YouTube, those are the free ones. You can also become a member if you want to see the full videos as well. So, without further ado, let's give a rundown on Maxwell's theory and gauge theory. So we're almost done here with developing an action for our quantized gravity model. Previously, we came to a form of the canonical position variable that resembled that of the electromagnetic potential in Yang-Mills theory. Right, we haven't talked about Yang-Mills theory yet, but that's going to be the next video. In this discussion, we will briefly go over Maxwell's theory. Right, so not Yang-Mills. I was a little bit too excited there. We're going to go over Maxwell's theory today, and then in the next video we're going to go over Yang-Mills. So let me just change the thickness of my pen here really quick. Today we're doing Maxwell's theory. And to understand this model better, we need to come back to our quantum gravity model. So we are going to start with our EM Lagrangian. So if you're not aware, our Lagrangian, our massless Lagrangian, is this guy right here. So these two guys are our electromagnetic field strength tensors. Okay, so we can expand these two guys to look like this, right? So we have our temporal form extracted out of our spatial forms, or another way of saying this is our magnetic components separated from our not our magnetic, right? So this is our electric components separated from our magnetic components, right? So these are the electric. Let's do it like this. Let's do this in a different color. I associate electric with this color. And then our magnetic components. And we have a 2 out there, right? Because these A's can also be 0, but they're the same value, and so why we get that 2, and so we end up with this, and then we end up with this here, right? Because the definition of our electric, or our field strength electromagnetic tensor, is this derivative here. Okay, so it follows that a change in our Lagrangian is going to be a change in the integral of Lagrangian density. So all of this is going to go inside here. And then we want to emphasize something. We want to emphasize this term and make this term irrelevant right now. So this symbol here is called the superset. So the change in our Lagrangian is a superset of this guy right here. So it's this. This is what this is saying is that this thing is inside of this thing, right? Because it's this minus this bit. So this thing we at least know is part of our Lagrangian. Okay. So we're going to call it this for right now and just ignore this part. And when we do that, we can actually take the change now, right? So that we can think of this as a derivative, and so the this is just product, or this is chain rule, right? So this cancels out with the 2 because we bring that over. This is calculus, okay? But then we take the derivative of the inside, which is this guy right here, and then what we end up with is this guy here, and then this right here. The superset symbol means that the change in Lagrangian contains the argument. Okay, we just talked about that. we're going to define the canonical momentum of the system, therefore is this thing. Right, so if this is our Lagrangian now, and we're defining our canonical momentum to be this thing, which is, we've sort of come across the concept of a canonical momentum now. So I don't want to say I shouldn't have to explain this, but we're familiar with this, at least to some extent, this prescription. We can therefore say that our canonical momentum is this guy right here, right? Because we take this here and then divide by this thing, which is right here, okay? And then this thing here is just a Kronecker delta, right? It's a Kronecker delta over A and B and over X and Y, right? So we have two Kronecker deltas, one three-dimensional Kronecker delta over these two positions and then over our indices as well. And so what that's going to do is that's going to drive this B to an A and then drive this B right here, right? So this B being driven to an A and this Y is going to be driven to X. Okay, so we have this, all right? And then we get, because this is over X and this is over Y, we can ignore the integral, and so we have this, and so from here we get this. So our electromagnetic field, or our canonical momentum, I shall do this in red, our canonical momentum is equal to this thing, which is equal to this thing. Everything comes down to our potential. Our 4 potential, right? This is, everything comes down to our 4 potential. All right. If we define this guy here as the electric field vector, which we can do, right? Because F mu nu is equal to our 0 along the diagonals, and then E along these ends, and then B's along the other ends there, or within off the off diagonals as well. The 0A, well, that's just the electric component. So what we could say is that the canonical momentum, this guy here, is equal to this guy here, which is equal to, we're saying he's going to be equal to the electric field A. So we have that our canonical momentum is our electric field. Okay? We can derive the relationship between the canonical variables. However, because this is a brief on Maxwell's theory, we're not going super deep into this. I'm just gonna give you the relationships right here, right now. Okay, we can derive these, but that would make this video way too long. We're already 8 minutes into here, and I think I have like 3 slides on this. So we're just gonna give it straight up. I don't think it's too difficult to comprehend because we've seen this kind of stuff before. I've done this. I think I've actually done this derivation on my No Nonsense Quantum Field Theory playlist. However, if I haven't, I can do this in a separate playlist. I'm sort of right now developing in-depth quantum field theory again, because there are some things in my other playlists on quantum field theory that I want to add, make things more in-depth. But with that being said, here are the canonical relationships, right? So we have our potential and our, so this is our canonical variable, this is our canonical momentum, right? So, and then this is our variable with our momentum and our variable with our momentum. And the 0th components, the temporal components, right? And then the indices. And so really what this comes down to, like really what this comes down to is this guy right here, okay? So this is something to keep in mind. From these relationships, we can perform a Legendre transform on the Lagrangian to get the canonical Hamiltonian. And so let's take a look at that. We're going to say that our canonical Hamiltonian, C, our canonical Hamiltonian H, is going to be equal to this. And we've proposed this thing, okay, our EM Lagrangian, to be this right here, okay, and this again comes from this right here, right, this guy right here, because these 0 A's we said were related to this canonical momentum, right? So from here to here, that's the relationship, right? So our canonical momentum and the magnetic part. Then we came up with this relationship. We just did this, derive this relationship, so we could plug that into here, and we get this guy now, right? So this one's here, and then this guy here, right, is going to be this. We just make this replacement, okay? Then from here to here, we understand this to be this thing here. This is something we learn in calculus. This is integral by parts, okay? And so what that does is it gives us this term here, this derivative of A naught, or A0, times this thing. We're just flipping the derivative when we do that, okay? And this guy is right here, and this is squared, right? So squared, 1 minus 1/2, well, that's positive 1/2. Okay. This Hamiltonian works in giving us the same result for a canonical Hamiltonian, or for a canonical momentum. Okay, so this is where things get a little bit, maybe a little bit more complex, but I'll try to break this down. So whenever we take the Poisson bracket with our Hamiltonian, we get a time derivative of that thing that we're taking the Poisson bracket with, right? So if we're taking the Poisson bracket, which is this thing, of some object, it can be any object, with a Hamiltonian, then we get this, okay? This is a fundamental rule. We can actually derive this, but again, this is not a brief on Poisson theory. This is a brief on Maxwell and Gauge theory. And so, what we can do is we can divide both sides by pi b, right? Pi b, and then we get, or not divide both sides, right? We're dividing by 1, or multiplying by 1, essentially, right? We have pi b and pi b. These are just small changes in each other. This is a canonical Hamiltonian H, so there should be an HC in there. And so, a small change in HC, this thing, well, we said that was up here, right? So we can, we'll write that down, a small change in all of this, okay? And this thing, again, is inside of this guy, right? Because, all right, so this thing is actually inside of this guy. This is a superset of this, right? Because this is added again. So because this is added, this thing is bigger. This thing is inside of it. So this thing is still part of the Hamiltonian. It's just not the full thing, right? But we're doing this because, again, this doesn't have a canonical momentum term in it. This doesn't have this thing in it. So we're just going to ignore that, okay? And so we get this. And then from here to here, we have this, right? So we're taking the change, right? So a small change. So this is, again, the chain rule. And then here we have the chain rule as well. And so we get this. And then we have, so then we could say, well, if we want to divide our canonical Hamiltonian, by this thing, right? So that is that's going to be, so we have this guy here, right, so that's this guy. So this here and this here is this guy here. We're dividing, let's get a blue color, this guy here, this guy here. So you can kind of see how this works, right? So we're bringing these two guys out here, and then we're dividing by this. And then we have this guy, right? So from here to here, well, this is just a Kronecker delta over y and z, and c and b, right? So y and z and c and b, and so we're driving now indices to, this is going to be driven to b, this is going to be driven to b, and these two guys are going to be driven to z, and because we're having an integral over y, we don't have to do the integral, and so we have this here, right here. So, okay. And this is, our Hamiltonian works in giving us the same result for our canonical Hamiltonian. This is our canonical Hamiltonian. And so, what we can do now is, let's go over to this green box. We can calculate the time evolution of the canonical momentum and use this result to solve for the electromagnetic Hamiltonian. So let's do the same thing here. So we did this for our four potential. Let's do this for our canonical momentum now. So for the canonical momentum, same thing, right? So divide both sides, or multiply both this by 1. And then here we have, since these are canonical variables, a Poisson bracket between two canonical variables, well, that's just going to give us Kronecker deltas, okay? And when you do this, you'll find that there's a negative in here, and so we get this guy right here. So now, okay, so let's just keep on going here. So our Hamiltonian, or canonical Hamiltonian, right here I wrote EM Hamiltonian, but this is actually canonical, right? Because we have our canonical variables in here, canonical variables. And so let's just make this a C. And so, but really it doesn't really matter, right? This is it's just a label, right? This is just telling us that this is our canonical Hamiltonian. So our Hamiltonian written in canonical variables. And so superset again, because, and I think I skipped a step here just to save some space, but again, this guy does not have a canonical term in it, and so we're left with this guy and this guy. And let's see here. FAB. Oh, actually, okay, so actually what we're doing here, so we're leaving out these two terms, right? It's because, so this guy is actually this guy, right? And this guy turned this guy into a 2, right? Because of the chain rule. We left out these two guys, and we just said that this is a superset. Again, this thing is bigger than this thing, okay? Because we're adding this guy here, and we're sort of subtracting this thing here. But this thing is actually going to be larger than this thing. And so we're calling this a superset. We're calling this thing a superset of this thing. So this thing is inside of this thing. I think that's the best way of understanding this, is that a superset is inside of the thing that you started with, right? So this thing is, let's undo that. This thing is inside of this thing. And so we can say that this is our Hamiltonian for all intents and purposes. And then, so we expand this guy out, right? So to get this, and then from here to here, right? So we have FAB delta AB, and then we have this 1/2 FAB delta A, and then we have these derivatives. These are all, so these two terms are essentially the same thing, which is how we get rid of this 2. okay? The only difference here is that we have A and B and B. So because of anti-symmetry rules, this guy can effectively become a positive, which is how we get this. Using two boxed equations, right, so this guy here and this guy here, we get this here, right? So our canonical Hamiltonian is this thing, right? So that's going to be this guy here. That's our second box, and then this comes from our first box. And then we have this, right? Because we're driving this thing is these two terms give us Kronecker deltas that drive C and B to A and B. And then this stays a B. And so the green box, right? So in this whole green box here, we can relate the spatial field tensor with the magnetic field tensor. And so we have that this guy here, we're going to say this guy is equal to this guy. Okay. And the reason we're doing that, in the green box, we can relate the spatial field tensor with the magnetic field tensor. This guy here, right? So the canonical, so this thing here is this guy right here. Right now it seems a little bit unintuitive why that's the case, but we're gonna get there in just a few seconds here. Together we have the Ampere's law of electromagnetism, right? So this guy here is the time derivative of, wait for it, time derivative of this guy, right? Because when we take the time derivative of this, well, that's just that dt, right? And that is right here. And then FAB, well, this here is this guy here, and then FAB we'll say is this guy. And so this is actually, so this thing here is B, because we have this. And then this guy here is this guy, and then we just showed this thing. Right, so really, all in all, this math shows us that we can actually derive Ampere's law of electromagnetism. We can do the same with Faraday's law of electromagnetism, by first starting with finding the time evolution of FAB. Right, so time evolution of FAB with our Hamiltonian, we get this, same sort of process we've been doing before, and then we get this here, because we calculated this guy to be this right here, where this is this right here, right? Because this here is just this, and so we can take the derivative with respect to AC as we're doing for both parts of the numerator, and we get this here. So we have a bunch of Kronecker deltas. Okay. Substituting back, we have that the derivative of FAB is going to be this. Right, so that's this times this, which is right here. All right, so we multiply all this, all these Kronecker deltas, right? So we're really just driving different indices to each other, but then we get this, and from here we get this here, right? So we have the derivative A with this guy, and then derivative A with this guy that's going to be here, right? So this guy is this one, this guy is this one, and then we have, let's see, we're subtracting let's see, we're subtracting this guy here. This should be at x and z, and so we have dz. So we have x. Let's see. So this is us just performing the integral. Okay, so skipping a few steps here just to save time is what I'm doing. But because of this guy here is why we have this twice. Okay, and then we have these two guys canceling out, right? Because this is going to be plus this, and this can be minus that. So in the end, we have this guy here, and this all checks out, right? Because FAB is this thing right here, right? So AB, AB, BA. Okay, so I can understand. So going from this step to this step, I should have that this is doing the integration. You can pause the video if you want and do this integration yourself. But really what this is we're integrating this, and then we're applying this as well. So applying the relationships that we defined, we get this, right? So this here is this, right here, this here is this. Equivalently, so this is the time derivative, this dot again, which is this right here, and we bring the minus over here, and then this, all this over here is just this guy right here. And this is Faraday's law of electromagnetism. So we've actually derived Ampere's law, we've derived Faraday's law, all from canonical form, right? All from using this thing and this thing. And let's recall now that we have what we've done. We've defined the Hamiltonian for our system to be this guy, which is all of this. Then we found that identifying different parts of the conjugate momentum, we were able to recover Maxwell's formulation of electromagnetism. And so this dot is this, and then this alone with no dot is going to be this. We can see that the electromagnetic field components are just the canonical momenta associated with the electromagnetic field potential. So let's also recall the gauge transformations associated with this theory. And this is where gauge transformations really start playing a role here. So that we have this law here and we have this law here. Well, let's cover this one first, right? So the gauge transformation is this thing, is where you add some derivative of some scalar object, okay? This is a transformed Ford potential, which is this transformed Ford potential. And when we do that, we get this, and then the anti-symmetry in the epsilon tensor gives us this, okay? Because this guy here, because of the anti-symmetry, we have this, the j and the k and the j and the k. This whole thing is going to go to 0. And this thing here is what remains, which is this guy here. Okay. And so we can see that under the gauge transformation, the B turns into B, right? So there's no change in the values of the magnetic field under a gauge transformation. Similarly, with the electric field, we can do the same thing. We're gauge transforming A, just as we've done over here, right here, same gauge transformation. But we also are proposing that a gauge transformation has to be done on this object here, which is a scalar field. This is the Ford potential scalar field. And we have this, and so when we do this, we get the this derivative here, and then these two time derivatives, this time derivative of this, because these are just t and I and t of lambda, and lambda. These things are going to cancel, and we just get the time derivative of A and the spatial derivative of V. And then we have this, which is this, which is this. And so this is quite interesting. This type of transformation that involves adding and subtracting derivatives of an arbitrary scalar function while keeping the physical variables unchanged is called the gauge transformation. Maxwell's theory is therefore gauge invariant, and it carries this gauge symmetry. To get a full grasp on this, though, we want to understand the things that act as generators for gauge transformations. And to do this, we need to talk about Poisson brackets in more depth. So let's just cover Poisson brackets just a little bit, and then we're gonna sort of tie things back together. This is going to be somewhat of a longer video because we're doing Maxwell's theory in one video, right? So our Poisson brackets are defined in this way, right? So our canonical variables are swapped between the denominators here. So QP and PQ. This is really what makes, mathematically, this is how a Poisson bracket is constructed. For canonical variables, we get our fundamental Poisson brackets, right? So canonical variables between two Q's and two P's are going to be 0. And a P and a Q is going to be a delta on their indices, right? So K and L. And really what these P's and Q's are positions and momenta. Canonical positions, canonical momenta. We can promote a new set of canonical variables in this way. So big F, and big G, which are these right here. We can define, so this big G, we can multiply by big Q, or a total derivative in big G with respect to P, right, is going to be this here, right? Because if big G is a function, of P and Q, well, we can take its derivative with respect to big Q. Actually, so wait, it's not just a function of P and Q, right? It's a function of big Q and big P. Okay? And same thing with Q, but we're not going to do that here. So if we're saying that big G is a function of big Q and big P, and these two guys are a function of little q, well, we can do these guys. The reason we can do this again is you can sort of see these guys canceling out. We get these right here, right? And so same thing here, G's with Q's. And so now, okay, so what does this all mean? So we can rearrange things, and when we rearrange things, we have this GQ, or DG DQ, that's this guy right here. And this is FQ, and we have FQ and FP, right? So let's see here, because I skipped a few steps here. So this is going to be FQ, FQ, right? So, and then this is going to be, we're going to have P and a Q and a P, and a Q and a P, right? So if we, let's just erase that really quick, do a different color. So this here with this one, and then this one with QP, P, and Q. That's all this right here. So what I highlighted in red is that. Same thing for, if I do this in blue, let's see here, G, big G, how do I want to do this? So big G, big P, big G, big P, right? So that's this guy right here. And then F and P, right? So that's going to be let's see. Let's do, what color do I want to do? I want to do this. Let's do this color. F and P, right? So that's going to be F with this one, or so QP, and then this one with this one. So that's these guys. All right. And then we just rename things. So we're replacing G with F, and we're saying F is equal to QK. And so we just rename things. We get this. And then we can see that these guys are, this here is going to be 0, right? Because it's Q and Q, Poisson brackets. And so we're left with K and J as a Kronecker delta. So like this. We can see, that FQ is dF dP, and similarly FP is dF dQ, right? Because FQ, that's this one here, that's going to be dF dP, this one right here, right? So all the colors I'm using might be a little bit confusing. Let's do this color. So FP, that's this guy right here. And then the FQ is this guy right here. Right, so because again this guy went to 0, and we're saying that this is equal to this. Okay? So, and similarly, we can do the same process and we can see this one. So really what these Poisson brackets are doing is they're providing a different means to a derivative for some canonical variable with respect to some canonical variable. So you have some function, you Poisson bracket it with some canonical variable, and that's the same thing as taking a derivative of that function with respect to the canonical momentum of that associated variable. This tells us that the Poisson bracket acts as a means of the derivative. Within the Hamiltonian framework of Maxwell's theory, we can seek a function that gives us the gauge transformation in this way, and this is called a gauge generator. Right? So a gauge generator is going to be something that we place inside the Poisson bracket with one of our canonical variables, and we get the gauge transformation back. Right? So the gauge transformation is this guy over here. Where did we define it? Actually, we defined it over here, right? This guy right here. Okay. So this is our gauge transformation. This is the function, an arbitrary function that we place inside a Poisson bracket with our canonical variable. And the point is that we want to find the function that does that so that we can get our gauge transformation back. And these functions are going to be important because we're going to find them to be relevant in quantum gravity. So we're going to propose that the gauge generator looks like this, just out of the blue, right? But this is what's going to turn out is that this is actually going to work. So using the gauge generator, we will calculate its application to an arbitrary function of our canonical variables. So here's an arbitrary function of canonical variables, and we can, this is the gauge transformation of that arbitrary function. And so we apply this arbitrary function here to our Poisson bracket. We can do this, right? So this one is this. We're multiplying both sides by 1, essentially, when we do this, right? Okay. Let's continue. We're almost done here. promise. So the definition of our gauge generator is, we said, was this guy. Okay, so when we do integration by parts, we actually get this thing here. This thing here is Gauss's law. We're going to say this thing here is Gauss's law. This is, we're going to say it's approximately equal to 0, because it's a constant that's a really small, right? So this is Gauss's law. We're going to say this is 0, so that means we can interchange the derivatives here. We're interchanging this derivative, right, and not being applied to this, but being applied to this guy here. But we also have to switch negatives or switch sign when we do that. Okay, so therefore we get this thing here, right? So this thing divided by delta pi z, that's this. We're dividing by delta pi z, right? So like that. It's a canonical momentum. And then we get this, and then we get this, right? Because this, we're just using Kronecker deltas to drive indices and positions. And when we drive positions, we can essentially ignore the integral, and we get this thing. And then we can now apply the gauge generator to the gauge for potential to get an expected result. And that expected result, right, so we start here. Again, we can think of these guys as canceling out, so that's why we're essentially multiplying by 1. Okay, we're multiplying by 1 here. You know, I'll actually write that down. I've been saying this constantly, but that's really just multiplying by 1. And then we get this, again, just because we defined, this is between two canonical variables, and we defined this guy by up here, and so when we do that we get this. And so this is our gauge transformation, right? Because over here we added a derivative of this scalar function. So what this means, what this is telling us, is that what we proposed over here actually works as a function. This thing here actually works as a function that drives, or that takes a derivative essentially of this guy here, and gives us our gauge transformation back. Alright, so our proposed gauge generator works in obtaining gauge transformations. We looked at the gauge dependence of the gauge potential. For sake of time, we're not going to prove the gauge independence of the electric and magnetic fields, but here they are. So we have the function applied to the electric field, the function applied to the magnetic field, and the function applied to the forward potential field. We proved this guy, and we can prove these guys in a very similar way we've been doing, but we're not going to do that just because we're like 45 minutes into this now. But this is, again, these two guys are related to our conjugate momentum. So we now have formulated our theory entirely from Poisson brackets and a generator function. This generator function is the real driver of all electromagnetism because it has a non-zero effect on the potential and zero effect for the canonical counterparts. And just reminding ourselves, these things, the electric and magnetic fields, are gauge independent, right? Because they have this gauge symmetry in them. When we apply the gauge symmetry, we get them back. We get the transformed equations back. And so this means that we have gauge symmetry. This is the essence of what gauge symmetry is. So in canonical form, we have developed Faraday's law, Ampere's law, and Gauss's law of electromagnetism. In this form, it's easy to see that the canonical momentum to the potential is the thing that gives rise to the laws of EM that we all know and love. And so this is the relationship between the two canonical variables. This is Faraday's law in canonical form. We've seen this. This is Ampere's law that we've derived, and this is Gauss's law. And with that being said, we're on 45 minutes here-ish. My dog starts barking. That's my cue to leave. And so with that being said, I hope you guys like this video. Make sure to like and subscribe. Make sure to go onto my Patreon page if you want to support the channel. And with that being said, you can also become a member. And I'll see you guys in the next video.